Hello everyone, how are you? I hope that you all are doing fine. I am Aman sir here, and our today's topic of discussion is the basic concept of unit, dimension, the universal constant, and also some concepts about the graphical presentations that is required in the study of physical chemistry. You will find in the introductory part or in the appendix part of any textbook of physical chemistry or physics that there is the concept of unit and dimension in all these books, because this is the fundamental part or the fundamental thing that is always required prior to the study of physical chemistry or physics. So let's begin with the 7 basic quantities which is approved by the Standard International, that is SI, and with the help of all these 7 basic quantities you can make any other secondary quantity. So what are these basic 7 quantities? These are the length, mass, time, temperature, electric current, luminous intensity, and amount of substance. Here it is electric current, not electric charge. Electric charge is not the basic SI quantity. Actually the basic SI quantity is electric current. Okay, so we shall make interconversions where all these primary or the basic quantities will be utilized in order to make the secondary quantities, such as electric charge with the help of electric current. How we shall do this? So these things will be very much carefully discussed here, and you also have to be very much careful about the case sensitivity of the symbols of the quantities as well as the symbol of the SI units. Okay, so what about the symbols of the SI quantities? First of all, the symbol of length is capital L. This is capital L. That of mass is capital M. That of time is capital T. That of temperature is theta. Electric current capital C. Luminous intensity capital I, and amount of substance small letter n. Now what about their corresponding SI units? Their corresponding SI units are: for length it is meter, for mass it is kilogram, for time it is second, for temperature it is Kelvin, for electric current it is ampere, for luminous intensity it is candela, and for amount of substance it is mole. Now these SI units also have their symbolic presentations. For meter it is small letter m, for kilogram it is small letter k followed by small letter g, for second it is s small letter, while for Kelvin it is capital K. Okay, and for ampere it is capital A, for candela it is CD small c small d, and finally for mole it is MOL. So MOLE, mole, is the name of the unit, while MOL, mole, is the symbol of that unit. Next is the conversion of the other quantities from the which will be derived from the basic 7 SI quantities. So let's begin with area. So area of some surface which has the mathematical definition length into breadth. That means length has the dimension of L, that is length. Breadth also has the dimension of L, that is length. So its equation should be length squared. So the dimension has the symbolic presentation capital letter L squared, and its corresponding SI unit should be meter squared, and symbolically it should be represented as small letter m squared. This way, for volume, length into breadth into width, its equation is length cube, dimension is capital letter L cube, and the symbol of the SI unit is m cube, small letter m cube, that means meter cube. For density, when mass is divided by volume, that is the mass of unit volume, which is the definition of density. So its equation should be, in the numerator there should be mass, and in the denominator there should be length cube, because the dimension of volume we have just obtained, it is length cube. So how they will be symbolically represented? They will be symbolically represented by capital letter M, capital letter L cube inversed, and its symbol of the SI unit is kg per meter cube. Similarly, distance or displacement. Okay, this is the actually linear measurement. Distance means the path covered and displacement is the linear distance, aerial distance of the initial and the final position. So both of them should have the dimension of length, and the symbol of length is L and the unit is meter. Similarly, speed or velocity. Speed is actually distance by time, that means path covered by time, and the velocity is actually displacement over time. But both has the dimension in the numerator length and in the denominator time. Therefore, the symbolic presentation of this SI of the dimension of distance of speed or velocity should be capital L, capital T inverse. That means L by T, and the unit should be meter per second. Now, acceleration, the rate of change in velocity with time. So when velocity change is divided by time, then you will get the definition of acceleration. So how it is represented by means of an equation? It is represented by length by time squared. So the symbolic presentation of the dimension is L over T squared, or L T square inversed. So the corresponding SI unit should be meter per second square. That means m dot s to the power minus 2. Our next quantity is force. So what is the definition of force? Force is actually the product of mass and acceleration. So its mathematical equation should be mass in the numerator and accelerations, just we have obtained length by time squared acceleration. So the dimension should be ml t to the power minus 2, and the SI unit should be kg meter per second square. That means this is called actually Newton. After force, we arrive at work or energy. Both have same dimension, same unit, work or energy. Work is actually the product of force and displacement, and energy is the efficiency to do work. So both should have the same unit and dimension. So the equation should be mass into length squared in the numerator, and in the denominator there should be time squared. That means force, okay, force is actually mass into length by time squared. So when this dimension is multiplied with length, that is displacement, then energy or work is obtained. So the dimension should be ml square by t square. So the corresponding unit should be kg meter square per second squared, which is known as joule. Our next quantity is power, which has the mathematical definition of rate of doing work per unit time. So when work, this dimension, mass into length square by time squared, is divided by time again, then you will arrive at this equation, which is mass into length square by time cube. Okay, so the corresponding symbol of the dimension should be ml square t cube inverse, and the corresponding SI unit should be kg meter square per second cube, which is actually known as watt. But our next quantity is very interesting, which is known as action, which is actually defined as the duration of doing work. That means when work is multiplied by time, that is the product of work and time, it is known as action. Okay, so the definition should be what? The equation should be what? This part multiplied by time. So instead of mass length square by time squared, it should be mass length squared by time only. So the corresponding symbolic presentation of this dimension should be ml square t to the power minus 1, and here you find it is kg meter square per second, that is joule second. Do you know in which constant we use this unit, joule into second? Okay, let me tell you, it is Planck constant, 6.626 into 10 to the power minus 34 joule second. So that unit is actually the unit of action, and when this h is multiplied by nu, that is 1 by time, then this time part is cancelled and only joule part is left. That means you reach the dimension of energy, that is h nu has the dimension of energy. So this is a very interesting quantity, action. Next is tension. Tension is force per length. Okay, suppose you are pulling some rope or pulling some thread. Okay, so the force applied in the perpendicular direction to the thread or the rope per unit length is actually tension. Okay, suppose it is the surface of water, you have put some thread on it. Okay, then on that thread, in each perpendicular direction there is some force acting on it. Okay, and this force per unit length is actually known as surface tension. How you will measure this? It is very easy. You make a film, okay, on a loop and then put a thread on it and pierce any one part at any side of the loop. That will be destroyed, and there will be a crescent type of shape in the film, and there from the thread towards the film there is some force which is acting in the perpendicular direction on the thread, and that force per unit length is called tension. Okay, so when force is divided by length, that is, here is force, mass, length by time squared, so length will disappear, will be cancelled, and mass by time squared will be left. So mass by time squared, actually force is Newton and length is meter, so it is also Newton per meter. Actually it is kg per second squared. Okay, after tension we move to momentum or impulse. So you know, you all are very much familiar with the definition, mathematical definition of momentum. It is mass, it is the product of mass and velocity. Okay, so mass, this is mass, and velocity is length by time, so ml t to the power minus 1 and kg meter per second. And when you know the second law of Newton's law of motion of Newton, the rate of change in momentum is what? It is force, isn't it? So if this is divided by t, it will become ml t square inverse. This is actually force. Okay, next we have some more quantities. Suppose it is pressure. Okay, pressure is defined as force per unit area. So force means mass over length over time squared, and then actually mass into length by time squared. Then when it is divided by length squared, then it will become mass over length by time squared. Okay, so it should have the dimension ml inverse t square inverse. This is actually without any use, this bracket closure, so ignore this, and the corresponding unit kg per meter per second square. You know what is this unit known as? This is known as Pascal or Newton per meter squared. Electric charge, as I have said, that with the help of electric current we shall make the unit of electric charge. So electric charge is defined as the duration of electric current. Okay, so duration of electric current means it is actually the product of electric current at time. So electric current into time is the equation. So electric current is C, time is t, so its unit for electric current is ampere, for time it is second, so ampere second. So 1 coulomb is actually 1 ampere second. Potential difference. In the basic 7 quantities there is no mention of potential difference, so it is a secondary quantity that should be obtained from the basic 7 quantities. So what is its definition? When electric charge is multiplied with potential difference, then you will get energy, isn't it? So when energy is divided by electric charge, you will get potential difference, and energy has the dimension mass into length squared by time squared, and electric charge has the dimension electric current into time. Okay, so when electric current into time is divided by the dimension of energy, you will get the exact dimension of potential difference, which is known as 1 volt, and 1 volt is actually 1 kg meter squared per ampere per second cube. Okay, and this is actually nothing but joule per coulomb. Next, it is resistance. So remember the Ohm's law, V equals to IR. That means V is potential difference, I is electric current, and R is resistance. So when you want to obtain the unit of R, then you have to divide V by I. That means potential difference by electric current. Potential difference has this unit, mass length square by time squared into electric current into time, okay, in the denominator. But when another electric current is added here, the electric current becomes electric current squared, okay. Then you will get the dimension of resistance. So mass m, length squared means L squared, by time squared into time, that means by time cube, by electric current squared, that means C squared inverse, okay. So m L squared, C squared inverse, T cube inverse, and the corresponding unit is kg meter square per ampere square per second cube. So what is 1 volt? 1 volt is 1 kg meter square per ampere square per second cube. Very interesting. Now molar mass or molecular weight. You all do not mention, never mention the unit of molar mass. Suppose oxygen. What is the oxygen unit of oxygen? It is 32 unit. But that is wrong. In the SI convention, this is 0.032 kg per mole. If you say it's 32 and do not put any unit, then it is wrong. Then how can you make it correct? You have to mention that it is gram per mole. So it has definitely some unit, molar mass. So when mass is divided by amount of substance, that means in the equation, in the numerator you have mass, and in the denominator you have amount of substance. Okay, then you will get the dimension m, capital M into small n inversed. So the unit should be kg per mole. Okay, very simple. Now frequency is number of cycles per unit time. That means equation, by means of equation it is time inversed. So t to the power minus 1 is the dimension, and s inverse, second inverse, is the unit. Similarly, wave number is another unit of frequency, which is number of cycles per wave. That is, but at a particular distance, how many cycles have been completed. That means when wavelength is reciprocated, then the reciprocal of wavelength, this is called the wave number. So this is also the unit, actually the expression of frequency, which is known as wave number, and the dimension is length inverse, and the corresponding unit is meter inversed. Now these units are all SI units, but we have some other conventions like CGS or FPS. The full form of CGS is centimeter gram second, FPS is foot pound second. So there are some other usual units also. So we have to convert these SI units into other units. Let's start from force. Force as the SI unit Newton. So if it is 1 Newton, then it is actually 1 kg meter per second square. That is 1 kg into 1 meter divided by 1 second whole squared. That is, instead of 1 kg, you have to put 1000 gram. Instead of 1 meter, you have to put 100 centimeter. And second remains unchanged because it is common in both conventions. So the result is 10 to the power 5 dyne. dyne, dyne is the name of the CGS unit of force, and dyn, dyne, small letter, is the symbol of CGS unit of force. Next parameter is energy or work. Energy has the SI unit joule. So if it is 1 joule, then it is actually 1 kg meter squared per second squared. That is 1 kg multiplied by 1 meter whole squared divided by 1 second whole squared. So just put the corresponding values, then you will get 10 to the power 7 arg. So arg is the CGS unit of energy. Next is different units of pressure. The SI unit of pressure is Pascal. It is written sometimes as capital P small a, or it is also allowed small p small a. Both are correct. This is actually nothing but Newton per meter squared. Now its CGS unit should be, instead of Newton you can write dyne, and instead of meter squared you can write centimeter squared. So the CGS unit of pressure is dyne per centimeter squared. What about its other usual units? Lot of usual units such as bar, PSI, pounds per square inch, kg per meter squared. You know about PSI? This is the convention of measuring pressure of the tires of automobiles. Okay. Atmospheric pressure or standard pressure of the atmosphere, Torricelli or torr, or height of mercury column in millimeter or millimeter Hg. So these are the different units of pressure. Okay, now we have to interconvert them. Like if it is 1 Pascal, then 1 Pascal means 1 Newton per meter squared. That means 1 Newton divided by 1 meter whole squared. Now we know that 1 Newton is actually equal to 10 to the power 5 dyne, and 1 meter is 100 centimeters. So it is 100 centimeter whole squared. That means the calculation is 10 dyne per centimeter squared. So 1 Pascal, that is 1 SI unit of pressure, is actually 10 CGS unit of pressure, that is dyne per centimeter squared. Similarly, 1 bar is defined as 10 to the power 5 Pascal, or 1 lakh Pascal, or 0.1 million Pascal. So the relationship is 1 bar equals to 0.987 atmosphere, while 1 atmosphere is 760 millimeter Hg, that means 760 torricelli, or 76 centimeter Hg. So from the formula H rho G, H is the height of the liquid column, rho is the density of the liquid, and G is the gravitational acceleration. So the height of the liquid column of mercury is 76 centimeter, while the CGS unit of density of mercury is 13.6 gram per cc, while the CGS unit of gravitational acceleration is 981, and accurately 980 into 980.665 centimeter per second squared. So when this is calculated, the product is 1013250 dyne per centimeter squared. And if you convert this into Pascal, then just divide this by 10. Okay, then it will become 1013225 Pascal. Okay, 1013225 Pascal. Or if you divide this by 10 to the power 5, then it will become 1.01325 bar. Next, interconversion among different units of pressure, it is still continuing. There is another unit of pressure. If you pulling a mass of 1 kg, then the pressure in your hand is 1 kg per meter squared. If the surface area is 1 meter squared, then it is 1 kg per meter squared. So 1 kg means 1 kg weight actually. That means if it is mg, then actually the force is 1 kg into 9.8 meter per second squared. That means 9.8 kg meter per second squared. That means 9.8 Newton per meter squared. Okay, so this is actually 9.8 Pascal. So 1 kg per meter squared is 9.8 Pascal, or 9.8 Newton per meter squared. Similarly, here we know another convention, the relationship, that is 1 atmosphere is 14.7 psi. Okay, so if the pressure of the tire of your bike is 29.4 psi, that means you are just giving it 2 atmospheric pressure. 1 psi is actually 1 pound per square inch. That means 1 pound weight divided by 1 square inch. That is the mg value. That means 1 pound into the g value in terms of FPS unit. So 9.8 meter per second square is this SI value of g, and the FPS value of g is 32.2 feet per second squared. And when it is calculated, then it gives the result 32.2 poundal per square inch, because pound feet per second square is the unit of force in terms of FPS unit, which is shortly known as poundal. So it is 32.2 poundal per square inch. And we also have another relationship, 1 psi equal to 6894.8 Pascal. Other units of work and energy are calorie and liter atmosphere, and we already have the CGS unit of energy, which is arc, and calorie and liter atmosphere. What about them? 1 calorie is 4.18 joule, while 1 liter atmosphere is 1 decimeter cube. That means 1 liter into 1 atmosphere. And we know 1 atmosphere means 10135 Pascal, and 1 decimeter cube means 0.1 meter whole cube. So it is actually 10135 kg meter square per second square, or simply joule. No, it's not joule, it should be liter atmosphere. Yes, definitely it's joule. Yeah, kg meter square per second square. So it's 10135 joule also. That's correct. Now CGS unit of electric charge. The CGS unit of electric charge is ESU, or stat coulomb, or in short STAT in small letter then capital letter C. It is the symbol of stat coulomb. and the full form of ESU is electrostatic unit. So the relationship is 1 coulomb. If coulomb is the SI unit of electric charge, then 1 coulomb is equal to 3 into 10 to the power 9 ESU. Okay, this way the charge of an electron is what? We know the SI unit, in SI unit the charge of an electron is 1.602 into 10 to the minus 19 coulomb, but in the CGS unit this should be multiplied by this value, that is 3 into 10 to the power 9. Then it becomes ESU or stat coulomb, that is 4.806, or in short 4.8 into 10 to the minus 10 ESU. Now suffixes and prefixes, actually if you go to larger units or if you go to further smaller units, then also you can use the same basic SI units, but you have to add some suffix or prefix before their names. Okay, so if it is 10 to the power minus 3 times than meter, then it becomes millimeter. So these are the fractions. If it is less than that original value, that is it is 10 to the minus 3 times or 10 to the minus 6 times, 10 to the minus 9 times, this way we shall add the prefixes such as milli, micro, nano, etc. Okay, so let's proceed. If it is 10 to the minus 3, then it is milli, minus 6 micro, minus 9 nano, this way nano, pico, femto, atto, jepto, yocto, up to 10 to the minus 24, it is yocto. And whatever the corresponding symbols, for milli it is small letter m, for micro it is micron sign of Greek alphabet, nano small letter n, for pico it is small letter p, for femto small f, for atto small a, for jepto small z, and for yocto small y. And for larger multiples, suppose it is 1000 gram, okay, then it is 1 kilogram, isn't it? Suppose it is 10 to the power 6 times greater than a hertz, that is the unit of frequency, then it is 1 megahertz. Similarly, you can add these other prefixes for larger units. So if it is 10 to the power 3, it is kilo, for 10 to the power 6 it is mega, and this way kilo, mega, giga, tera, peta, exa, zeta and iota. Okay, I repeat, kilo, mega, giga, tera, peta, exa, zeta and iota, and their corresponding symbols. For only for kilo it is small letter k, but for others all are capital letters, such as for mega it is capital M, for giga it is capital G, for tera capital T, then peta capital P, exa capital E, zeta capital Z, and iota capital Y. So the case sensitivity is very much important here. Suppose if you write PM, then if it is instead of small pm you write capital PM, then there will be an error of 10 to the power 27 times. How? Look this example. 1 meter is actually 10 to the power 12 picometer, as well as it is 10 to the minus 15 petameter. Now look this difference. Picometer is small p small m, but petameter is capital P small m. So 1 petameter is 10 to the power 15 meter, equal to 10 to the power 15 into 10 to the power 12 picometer, that is 10 to the power 27 picometer. So just replace this P with a capital P, then the order of your error would be of 10 to the power 27. And similarly 1 yotagram is actually 10 to the power 48. That means there are 48 number of zeros after 1. 10 to the power 48 yoctogram. So don't make any mistake for being case sensitive. Okay, if you put anything small instead of capital or anything capital instead of small, there will be a huge error. Okay, so this is about this slide, which is regarding prefixes. Okay, and some next part. So this is about unit and dimension. Now next part is some fundamental constants which you have to learn before studying physical chemistry or physics. So let's start with speed of light in vacuum. The exact value is 2.997925 into 10 to the power 8 meter per second, and we just simplify this as almost equal to 3 into 10 to the power 8 meter per second. Similarly, Planck's constant, as I have mentioned while discussing the unit of action, this is joule second. Okay, look the value 6.6256 into 10 to the power minus 34 joule second, and we simplify this as 6.626 into 10 to the power minus 34 joule second. Faraday means the electric charge of 1 mole of electron. So if you multiply the charge of an electron with the Avogadro number, then you will get this value. It is 96487 coulomb per mole. Okay, means Faraday means coulomb per mole, and we simplify this as 96500 coulomb per mole. Now normal molar volume, that means the volume at NTP. Okay, that means 0 degrees Celsius and 1 atmospheric pressure. This normal molar volume of 1 molar any gas, ideal gas definitely. This 22.4136 liter per mole, that is decimeter cube per mole, and simply it is 22.4 liter per mole. Charge of an electron or a beta particle, it is minus 1.602 into 10 to the minus 19 ampere second. Now one thing, during the discussion of unit of interconversion of coulomb into stat coulomb, this minus sign was not written. Actually that is the in that case I wrote the magnitude of charge. Okay, I omitted the symbol because that is also equal to the charge of a positron also, that is why. Okay, so we have to deal with the unit there, but here exact the charge, that is why this negative sign is meticulously written here. Okay, so this is minus 1.602 10 to the minus 19 ampere second or coulomb, and in the ESU unit, that is CGS unit, it is minus 4.8 into 10 to the minus 10 ESU. This is the CGS value of charge of an electron or a beta particle. Now some fundamental constants still continuing. Now charge of a proton or positron, this is plus, the same values. Okay, but the symbol is plus. Universal gas constant R, 1.987165 calorie per Kelvin per mole. Now calorie per Kelvin is also known as Gibbs, so it is 1.987165 Gibbs per mole. It has another value 8.3143 joule per Kelvin per mole, 0.0821 liter atmosphere per Kelvin per mole, because we know liter atmosphere is another usual unit of energy, and here joule, here calorie are the units of energy. Okay, and then it is divided by the unit of temperature and the unit of amount of substance. Okay, Boltzmann constant K, that is actually the molecular gas constant, isn't it? So if you divide this value of R with Avogadro number, then you will get this value 1.38054 into 10 to the minus 23 joule per Kelvin, or in short 1.38 into 10 to the minus 23 joule per Kelvin. Avogadro's number finally, it is N0. Some also write this as NA capital A. Some also write this as NA small a. Okay, here I will write this as NO or N0. The value, exact value is 6.022140076 into 10 to the 23 per mole. That is the unit of Avogadro number. Okay, and if we simplify this number, then it is simply 6.022 into 10 to the power 23 per mole. Next is rest mass of an electron, that is 9.10953 into 10 to the minus 31 kg. You have to memorize all these things, and the simplified form is 9.11 into 10 to the power minus 31 kg. Rest mass of proton, 1.67265 into 10 to the minus 27 kg, and in short 1.6725, okay, into 10 to the minus 27 kg. And rest mass of neutron, it is just little bit just heavier than proton. It is 67, it was 265 for a proton, for a neutron it is 495, or in short we write this as 1.6750, that means 675 only, into 10 to the minus 27 kilogram. Okay, or in gram you can convert this into 10 to the minus 24 gram. Here instead of minus 31, minus 28 gram. Okay, and permittivity of vacuum, epsilon 0 or E0, it is 8.854 into 10 to the minus 12 coulomb square per Newton per meter squared, and 4 pi epsilon 0, it is 1.113 into 10 to the minus 10 coulomb square per Newton per meter squared. Okay, and finally the Rydberg constant, it is 1.09776 into 10 to the 7 per meter. And Bohr radius, this is the final value, final expression here. It's 5.292 into 10 to the minus 11 meter, or in short 5.3 into 10 to the power minus 11 meter. Okay. Now what about NTP and STP in the old convention and in the new convention? As I have said that NTP is normal temperature and pressure, and the corresponding temperature is 0 degrees Celsius, that is 273 Kelvin, and pressure is 1 atmosphere, that is 1.0135 into 10 to the 5 Pascal, and standard pressure is just temperature change 25 degree from 0 to 25, that is 298 Kelvin, and pressure in the old convention, pressure is 1 atmosphere or 1.0135 into 10 to the 5 Pascal, and in the new convention of SI it is 1 bar. Okay, that means only 10 to the power 5 Pascal. But in our chemistry study, in most of our books, this old convention is used. Okay, 25 degrees Celsius and 1 atmospheric pressure. But in the 12th standard NCERT books or ICSE books, you will find that the latest values for NTP and STP, they may be changed. So there is a possibility of their changes. So for the latest values, consult the NCERT books. But in our lectures, we will be using these old conventions. Now move on to the graphical presentations. Okay, so here we are going to plot 8 graphs in total, and a set of 4 will be plotted in this sheet, in this slide. So here for the A graph, it is y equal to 10 to the power 10, and for the B graph, it is y equal to 10 to the minus 10. For C, it is e to the power minus x, and for D, it is e to the power x. Okay, so these are the graphical presentations. Here the minus y axis is absent, because if it is some positive value which has some power, whatever be the power, positive, 0, negative, whatever be the power, overall value can never be negative. So y can never be negative here. So the minus y axis is missing here. Okay, so what about the graphical plot? Y equal to 10 to the power x equal to A graph. So A, this is the A graph. From here to this way, it is increasing exponentially, increasing this way. Look, the movement of the cursor. This is the A graph. So representing y equal to 10 to the power x. At this point, where it is cutting the y-axis, the value of x is 0, but the value of y is 1. Because when x is 0, it is 10 to the power 0, that is y equals to 1. So this point is representing the two coordinates x equal to 0 and y equal to 1. Similarly, for we move on to B, it is y equal to 10 to the power minus x. So it will be the mirror image of the previous one. So this is the movement of B. It is negative exponential curve. Okay. This is the movement of the cursor. Follow this. This is the B curve. Okay. Now exponential. E to the power x. For e to the power plus x, it is D. This is D. E to the power plus x. So D starts above A, and at this point, it is common for all. It goes beyond A. That is, here A becomes above D curve, and here D becomes above A curve in the second quadrant, while in the first quadrant D is situated below A. Okay, and why this point is common? Because everywhere the power is 0, so the overall value of y is 1, so it is 0.1, 0, 1. And finally the negative exponential curve is e to the power minus x. Okay, and it is going like this. Here it is below B, but here it is above B. Here the value of y is gradually decreasing exponentially. Okay, so these are the 4 graphical presentations, A, B, C, D curves. Now the logarithmic graphs. Y equal to ln x, y equal to log x, y equal to log 1 by x, and y equal to ln 1 by x. Ln means log base e, and simply log means log base 10. Okay, ln, n stands for natural, so ln natural log. Here the minus x-axis is missing, because you cannot take the logarithm of any negative value, because that is undefined. That is why the minus y value is missing here. But the negative value of y is possible, because if it is less than 1, then it becomes negative, isn't it? So here this point is common. Here x, if you put the value of x equal to 1, it is ln1, log 1, log 1 by 1 means log 1, again ln 1 by 1 means ln 1. So the value of ln 1 or log 1, whatever it is, the value is always 1, always 0. So the value of y is always 0 for all the values of x equal to 1. So this point is representing the two coordinates x equal to 1 and y equals to 0, that is 1, 0. And all the curves will pass through this point. Okay, now look, this curve is logarithmic curve. A, y equals to, representing y equals to ln x, yeah, right. Now b, y equal to log x. We know that ln x is 2.303 log x, so ln x should be always greater than log x. Similarly, the log 1 by x and ln 1 by x are the mirror images of these two curves. So the mirror image of b is c and mirror image of a is d. So that's all about the today's lecture of unit dimension, constants, fundamental constants and graphical presentations. And finally, thank you. Have a